So now that we've introduced the concept to the unit circle, we're now going to talk about some properties of trigonometric functions. You'll notice that I'm saying functions rather than ratios. Now, when it comes to all of our trigonometric functions, we are inputting an angle, and the output is the corresponding ratio that we want associated with that, whether it's opposite over hypotenuse or adjacent over hypotenuse or whatever that happens to be. So when it comes to trig functions, when we refer to the domain, the set of all inputs for a trig function would actually be equal to the angle that we're putting in for these trigonometric functions. Now what we're going to do is we're going to break the angles, or break the ratios up into three different categories. So first one that we will consider is the sine of theta and the cosine of theta. Now, as a reminder, this is going to be y, and this is going to be x for any coordinate on our unit circle. Now, regardless of the angle that we use, we could spin around as many times as we want or use a negative angle or anything along those lines. There is never going to be an angle that we input, and we're going to wind up with a domain restriction. So the domain is going to be all real numbers. We can plug in anything. For the next category, I want to put the tangent of theta and the secant of theta together. I'm going to copy down what those ratios are and explain why these two things are going to be grouped together. So the tangent is defined as y over x, or the sine over the cosine. The secant is the reciprocal of the cosine, so it'll be 1 over x. You'll notice that in both of these cases, there winds up being an x in the denominator, which is a domain issue. So we need to make sure that x is not equal to 0, which is a fancy way of saying we need to make sure that the cosine of theta is not equal to 0. So what we're going to do is identify all of the points on the unit circle where the x-coordinate is 0 and say those need to be excluded from our domain. The first place where that occurs is up here at the ordered pair 0, 1, and it also occurs down here at the ordered pair 0, negative 1. Those two angles within the first rotation of the unit circle would be pi over 2 as well as 3 pi over 2. However, we can't just include pi over 2 and 3 pi over 2. We also need to include anything that's coterminal to either one of them. The next place where that occurs would be 5 pi over 2, or 7 pi over 2, 9 pi over 2, etc. Now, there are some people that would just say, well, we'll just call that odd pi over 2. So theta is not equal to odd pi over 2. But another way that you could say this is that it's not equal to pi over 2 and then every multiple of pi after that. So this is where k is going to represent some integer. K is an integer. And it's a fairly common notation there we go. K is an integer. Spelling is hard. So with that in mind, that would be our domain associated with this. And when we start graphing these things in a couple sections, we'll see some interesting things happen. Next up, I'd also like to put the cotangent as well as the cosecant together. Cotangent and cosecant go together because the cotangent is the ratio of x over y, and the cosecant is the ratio 1 over y. You'll notice that in both of these cases, it'll be necessary that y is not equal to 0, or more specifically, that the sine of theta is not equal to 0. Going back to our unit circle, the y-coordinate would be equal to 0 if we are at the ordered pair 1, 0, or negative 1, 0. So in the first full rotation of the unit circle, this would be at 0, pi, 2 pi, but we also need anything that's coterminal to these angles. So angles like 3 pi, 4 pi, 5 pi, and so forth and so on. Now this one's going to be a little bit easier to represent than the last one. We'll just say theta is not equal to k pi, where again k is an integer. I'm going to spell it better this time. Yes, nailed it. So these are going to be the domain restrictions associated with our 6 trigonometric functions. So basically, unless you're dealing with sine or cosine, you're going to have to keep your eyes peeled for these domains. Now, next up, let's talk about ranges. Now the output for these is going to be the corresponding ratio that we get from the unit circle. Now once again we're going to lump certain of them together, and we're going to start with the sine and the cosine. These two are going to have the same range. Now the sine on the unit circle is referring to a y-coordinate. The cosine is referring to an x-coordinate. So when we consider the range of these two functions, we're saying how far do x and y both extend? Well, x goes as far left as -1 and as far right as +1. Y goes as far down as -1 and as far up as +1. So the range for both of these two trigonometric functions is simply going to go from -1 up to +1. The next two that get lumped together for the range are going to be the tangent of theta and the cotangent of theta. Now this one's going to be a little bit more difficult to describe for now, and perhaps we'll give a better explanation in section 7.7. But for now you can take my word for it. Because x and y both range from -1 to +1, it is technically possible to create all real numbers for the range of both of those trigonometric functions. Now, as far as the secant and the cosecant are concerned, for the secant, we are taking the reciprocal of an x value, and for the cosecant, we're taking the reciprocal of the y value. Now, with that in mind, we're only talking about numbers that are between -1 and +1. So we're going to split that up into the negative numbers between -1 and 0, and the positive numbers between 0 and 1. If I take the reciprocal of a number that is between 0 and -1, it's guaranteed to be negative. The reciprocal of -1 is going to be -1. Oh, my comma's backwards. Oopsie poopsie. And the closer that this gets to 0, the larger in the negative direction this is going to get. We can actually make this as large as we want in the negative direction. By the same idea, the reciprocal of 1 is going to be 1. And as we talk about smaller values, the reciprocal is going to be giving us larger values. So large, in fact, that it'll make it all the way up to positive infinity. Again, we'll talk about that a little bit more in section 7.7. So next up, the periodic property. A function, f, is periodic with period equal to t if f of x plus capital T is equal to f of x, with t being as small as possible. So function f is said to be periodic with period equal to t if, mother ducking autocorrect, if f of x plus capital T is equal to f of x, with t being the smallest number possible. Now, all 6 of our trigonometric functions are going to be periodic because of the following. If we were to consider an angle on the unit circle, we'll call that theta, and if I were to consider another angle on the unit circle, which is theta plus 1 revolution, that would put me at exactly the same spot. So that tells me that the sine and the cosine are going to be equal to the exact same value if I talk about theta plus 1 revolution. Now, 1 revolution, if we're going to put this in terms of radians, is going to be equal to 2 pi. It is for that purpose that we can say the sine function has a period equal to 2 pi. The cosine function has a period equal to 2 pi as well. The reciprocals of these will have a period equal to 2 pi as well, because generally whatever happens to the sine and the cosine tends to happen to the secant and the cosecant as well. Now you'll notice from this list that there are two trigonometric functions that are missing. For the time being, I would like to refer to this guy right here as the ordered pair x, comma, y, right up there in quadrant 1. The two that are missing from this list are the tangent and the cotangent. Now, it is true that after 2 pi radians, the tangent and cotangent will repeat each other. But that is not the smallest possible value for the tangent and the cotangent. Here is the reason why. What we're going to do is consider a half revolution. Theta plus pi. The corresponding ordered pair that you would see down here in quadrant 3, this is origin symmetry, so it's going to change the x into negative x and change the y into negative y. It is because of that that if we were to consider the tangent of theta plus pi, this is going to be equal to negative y divided by negative x. However, when we divide negative y by negative x, that'll be the same as doing y over x, but y over x is the tangent of theta. It is for that purpose that tangent as well as cotangent have a different period. Their period is going to be equal to a half revolution, or 1 pi. When we start sketching the graphs of these trigonometric functions, knowing their period is going to be advantageous so that we know how much of the graph we need to create before we just say, and then the graph repeats itself. That's the idea behind this portion. What this is saying is that after a horizontal shift of t units, the y values will be repeating themselves. More on that to come. And last set of properties is going to be the even-odd properties. The even and odd properties let us know if these trigonometric functions are going to be odd functions or whether they are going to be even functions. Now, in order for us to determine this, we'll need to start with an input of theta with the corresponding ordered pair cosine of theta and sine of theta. Then we would need to consider what does the angle negative theta look like. Well, keeping in mind that theta, if a positive angle, will be a counterclockwise rotation, negative theta would go in the opposite direction. So the opposite direction would be this direction, with corresponding ordered pair cosine of negative theta and the sine of negative theta. Excuse me. Now, if we wanted to shorten this process a little bit, up here, this would be the ordered pair xy. Down here, as we move from quadrant 1 into quadrant 4, the y value becomes negative, but the x value stays as positive. So the question becomes, for each of our 6 trigonometric ratios, functions now, when I go from quadrant 1 into quadrant 4, is the trigonometric ratio staying positive, or is it becoming negative? If it becomes negative, it would be considered an odd function. If it stays positive, it'll be considered an even function. Excuse me. The only one of the big 3 that's going to stay positive will be the cosine. The x-coordinate is the only thing that stays positive here. So the cosine of negative theta will be the same as the cosine of theta because these two x-coordinates happen to be equal to each other. But if it's true for the cosine, it's going to be true for the secant as well, because the secant is 1 over the x-coordinate. The reciprocal of a positive quantity will stay positive. The other 4 trigonometric functions all become negative as we move from quadrant 1 into quadrant 4. So the sine, the tangent, the cotangent, and the cosecant would all be considered odd functions. Looking forward, that means that when we graph these odd functions, they will all have origin symmetry, and when we graph these even functions, they will have y-axis symmetry.